Hello everyone, I'm Sahadev Bharat and I'm going to be presenting the Physics 2211 Lab 3 report, which is regarding black holes and orbits. So our introduction is simple. We have two parts in this lab. The first part is creating the orbit of the star around a black hole and using this orbit to find the mass of the black hole. And our part 2 is to simulate an orbit using a spaceship, and the caveat is we must not crash into the planet or the moon that the spaceship is revolving around. The fundamental laws involved are simple. We have a universal gravitational formula which states that every particle in the universe attracts every other particle with the force along a line joining them. Newton's first law, an object will remain at rest or in motion at a constant speed unless an external force acts upon it, and Newton's second law, which states that the acceleration of an object depends on its mass and the force applied. Now, our main formula involved are as follows. We have the parallel and perpendicular components of the force, which is F net is equal to F net of parallel plus F net of perpendicular. We have the universal gravitational formula, which is this formula, and capital G is our universal gravitational constant. We have Newton's first law, which states that Rf is equal to Ri plus V average delta T, and Newton's second law, which is Vt is equal to V naught plus At. So our setup is simple. So the entire lab was a coding-based lab, and we assumed that only the forces acting on our bodies in both experiments were due to the forces in the program only, and we primarily use Newton's second law to compute the velocity and the position. So our part 1 is gravity due to the black hole, part 2 has gravity due to the planet and the moon. Our initial conditions in part 1 are as such: T max 86400, that's I think the seconds in a year or something. Then initial conditions in part 2 are as follows. And now the preview is simple. So we have the system, which is the star, the surroundings, which is the black hole and the universe. This is in part 1. And after computation, I determined the mass of the black hole to be 7.3 exponential times 43 kgs. Then for part 2, the system is the ship. The surroundings are the planet, the moon, and the universe, obviously. And the velocity in the x direction, which I determined after computation, is 2.55 exponent times 4 meters per second. And velocity in the y direction is 2.46 exponent power 4 meters per second. So this is our part 1 code for the black hole. So this is all given: gravitational constant, star mass of the star, delta T, time for observation. This is the arrows, which so we go here first. So we have the rate, we have V initial, which is all given to us. This is what we had to edit. So P initial, P final, we use the P is equal to mv formula. Then here, change in velocity formula, change in velocity and change in momentum formula. dp by dt was computed here. Here, F net is equal to dp dt was computed here. This was a bunch of dp by dt parallel formulae. And then we have using Newton's second law, which is from here, and then using that to calculate Newton's second law, F net perpendicular. And then this was the final formula to calculate the mass of the black hole, which is magnitude of F net times star dot position square divided by G times star M. And these were the arrows that I had to change a couple of values for in my actual diagram. So this is the video. So as you can see, we have the perpendicular and parallel direction, and the orange one is the one pointing to the center of the force. And we calculated the mass in the end. So now we're at part 2. So this was the masses and constants that they gave. Again, universal gravitation, planet mass, moon mass, ship mass, delta T, all given. These are the values I had to plug in. So after some trial and error, I determined these values. And these were the things I had to calculate. So we had F planet on moon, F planet on moon, F ship on moon, F net total, which is the sum of them. Then the same thing for the planet on ship, moon on ship, and then the sum. And then this was the Newton's second law position update formula and velocity update formula. So now we have the visualization here. So as you can see, the blue is our perfect orbit, and the purple is our moon, basically. And as you can see, it's in a perfect orbit, and we have our orbital speed and orbital period down there. So now let's look at our data. So the star, for part 1, the star goes into an elliptical orbit around the black hole, as we saw. The star speeds up closer to the black hole. When it's like closer to the black hole, it speeds up, and when it's far away on the right, it slows down. And the mass was calculated to be around 7.3 10 times 43 kgs. And for part 2, the ship first goes around the planet normally, as we saw in the previous slide. And then when it gets closer to the moon, the force of attraction disrupts, basically. It like kind of becomes weird because the moon and the ship become close to each other. And then the figure 8 orbit, which was given in the question, is quite challenging to achieve. So the errors, part 1, I possibly could have incorrectly coded the mass, and there could be some computational error. And in part 2, there were actually a lot of velocities and forces to calculate, so it's possible I missed something. And I feel like all of this pretty much boils down to coding or conceptual based errors. And let's look at our questions. So our first question was, if the net force and its parallel and perpendicular components are different from the rate of change of momentum, this is because we can observe certain changes in the change of momentum of objects, However, we cannot do the same for net force-based quantities of an object. Force of an object is calculated based on the observable quantities like momentum. And when we look at the dominant interactions that need to be involved in a computational model, is the force of attraction of the black hole, force of star, force of the moon, force of the planet. And out of all of these, obviously the black hole would be the largest. And that's pretty much it for my Physics 2211 Lab 3 report. Thanks a lot for watching and hope you all have a good day.